Welcome to the Deep Dive. Today we're diving into the world of carbon and its compounds.
Yeah, it's pretty amazing how much this one element impacts, like, everything around us.
Seriously, so where do we even start with something this big?
I guess we gotta start with the basics, like how carbon bonds with other atoms. That's really what makes it so special.
Right, bonding. It's all coming back to me now, kind of. Covalent bonds, right.
Exactly. Covalent bonds. It's when atoms decide to share their electrons instead of, like, transferring them like in ionic bonds.
Okay, so carbon's a share. Why is that sharing so important for it?
Well, you see, carbon needs 4 more electrons to be, like, totally stable, and gaining or losing that many is a real
I
challenge.
can imagine.
So sharing through these covalent bonds, it's carbon's way of getting what it needs.
So it forms compounds by sharing. Got it. Can you give me an example?
Sure, let's look at hydrogen, H2. Each hydrogen atom has 1 electron but needs 2 to be stable, so they share, forming a single covalent bond.
Okay, so that's a single bond. What about like double or triple bonds? How do those work?
Imagine oxygen, O2. Each oxygen atom needs 2 electrons to be stable. They share 2 pairs of electrons, making a double bond. And then there's nitrogen N2, which needs 3, so it forms a triple bond.
Wow, atoms are way more social than I thought. So how does all this bonding relate to the massive variety of carbon compounds out there?
That's where things get really cool. Carbon has this unique ability called catenation. Basically, it means carbon atoms love to link up with each other, forming chains and even rings.
So carbon can build these elaborate structures with itself. No wonder they call it the backbone of life.
Exactly. And to make things even more interesting, carbon is tetravalent. It means it can bond with up to 4 other atoms, not just other carbons.
Okay, I'm starting to see how catenation and tetravalency lead to so much diversity. But how do we tell all these different carbon compounds apart?
Well, one way is to look at whether they're saturated or unsaturated. Saturated hydrocarbons are like methane, ethane, and propane. They only have single bonds between carbon atoms.
So everything's all paired up in those. What about
Exactly.
unsaturated hydrocarbons? They're a little wilder.
You got it. Unsaturated hydrocarbons have double or triple bonds between carbons, like an ethene or ethene. These multiple bonds make them more reactive.
It's like a difference between a calm couple and a couple that's still figuring things out.
Yeah, that's one way to put it. And that difference in bonding really affects how they behave.
Fascinating. So we've got single, double, triple bonds, catenation, and tetravalency.
Yeah.
Is there anything else that contributed to the, millions of carbon compounds out there?
Oh, yeah, there's one more important player, heteroatoms.
Heteroatoms. Okay, now you've got my attention. What are those?
Basically, they're any atoms that aren't carbon or hydrogen that sneak into a hydrocarbon chain.
So if we have a chain of carbons and hydrogens,
Uh,
and we throw in an oxygen or a nitrogen, that's a heteroatom.
yep. And that little addition can totally change the compound's properties.
Okay, so we have carbon bonding with itself, making single, double, or triple bonds. Then we can throw in some heteroatoms. No wonder there are millions of these compounds.
Don't worry, though. There's a system to all this. Chemists have figured out a way to name these compounds so we don't lose track.
That's a relief. So how does this naming system work?
We use prefixes and suffixes to describe the carbon chain's length and the types of bonds, like methane. It has 1 carbon, meth, and then all single bonds. Ethane has 2 carbons, and again, all single bonds.
So the name tells us exactly what the molecule looks like. Pretty clever.
It is. And if there's a double bond, like in ethene, the ending changes to win. Triple bond, like in ethane, we use win.
This is starting to click. It's like a secret code.
Exactly. With practice, you can decipher these names and, picture the molecules in your head.
Okay, feeling a bit more confident navigating the world of carbon compounds now. But before we go any further, can you give us a final definition of each key concept?
Sure. Let's start with covalent bonds. A covalent bond is a chemical bond where atoms share electron pairs. This sharing helps them both become stable.
And catenation.
Catenation is when an element, like carbon, can bond with other atoms of the same element, creating chains or rings.
And tetravalency.
That means an atom has 4 valence electrons it can use for bonding. Carbon's tetravalency lets it bond with up to 4 other atoms, so you can see how that leads to a ton of different structures.
That's awesome. And lastly, heteroatoms.
Heteroatoms are just any atoms besides carbon and hydrogen hanging out in a hydrocarbon chain. They add some extra flair to carbon compounds, changing their properties and how they react.
Great. Now, before we jump into the different types of reactions, any questions for our listener about what we've covered so far?
Yes, actually, why do you think carbon's ability to form like all these crazy complex structures is so important for life? Think about the molecules that make up living things and what they do. We'll come back to this question later in our deep dive.
All right, we've tackled the basics of how carbon bonds. Now let's talk about the action. What kinds of reactions do carbon compounds go through?
Well, let's kick things off with a reaction we all know and love. Combustion.
Combustion, yeah. Big explosions, fire, heat, light, the whole shebang. But what's actually happening at the molecular level when something burns?
At its heart, combustion is a super fast reaction between a substance, like anything that can burn, and oxygen. And that reaction releases energy in the form of heat and light. When you burn carbon or carbon compound, it combines with oxygen, and you end up with carbon dioxide, along with all that heat and light.
So when I fire up my grill, the propane is reacting with oxygen in the air to make carbon dioxide.
You got it. And that's the reaction that's giving you the heat to cook those burgers. It's happening all around us, from burning a candle to, like, driving a car.
Wow, chemistry in action everywhere. Now, how's combustion different from oxidation? They seem kind of similar.
Yeah, combustion is actually a type of oxidation. But oxidation is a broader term. It happens when a substance gains oxygen or loses electrons. It doesn't always involve flames.
So like oxidation without fire. Can you give me an example?
Think about when you cut an apple and it starts to brown. That's oxidation. Or when iron rusts. Slower processes, but still a reaction with oxygen.
So oxidation is going on all the time, even when we don't see it. Pretty cool. Now let's move on to those unsaturated hydrocarbons we were talking about earlier. What about their reactions?
Right, unsaturated hydrocarbons, they're the ones with the double or triple bonds. They can undergo something called an addition reaction.
Addition reactions. Okay, so we're adding something to those double or triple bonds, right?
Exactly. The double or triple bond opens up, and new atoms or groups of atoms attach themselves to those carbons.
Can you give me a real-world example of how that works?
Think about margarine. Many vegetable oils are liquid at room temperature because they contain unsaturated fatty acids. Those have carbon double bonds. To make margarine solid, they use a process called hydrogenation.
Hydrogenation, yeah. Isn't that where they add hydrogen to make things more saturated?
Exactly. Hydrogen gas is added to those double bonds, turning them into single bonds.
Yeah.
And that's what transforms that liquid oil into a solid fat.
So the hydrogen atoms are filling in those gaps in the double bonds. Makes sense.
Exactly. That's just one way addition reactions can be used. We can tweak those carbon compounds and change their properties.
All right, so we've got combustion, oxidation, and addition reactions. What else is there?
Let's talk about substitution reactions.
Substitution, okay. Is that like when one atom or group gets swapped for another?
Right.
A trade?
You got it. This happens a lot with saturated hydrocarbons because they're not as reactive as unsaturated ones. One atom or group replaces another within a molecule.
So it's like a molecular switcheroo.
Yeah, exactly. And these substitution reactions are super important for making all sorts of compounds, from medicines to plastics.
Amazing how we can manipulate these molecules to create so many different things. Before we move on, can you give us a quick final definition for each of these reaction types?
Sure. Let's start with combustion. Combustion is when a substance reacts rapidly with an oxidant, usually oxygen, and releases heat and light. We know it as burning.
Great. How about oxidation?
Oxidation is when a molecule, atom, or ion gains oxygen, loses electrons, or increases its oxidation state. It's a big deal in lots of chemical and biological processes.
And an addition reaction.
An addition reaction is when two or more molecules join up to form a bigger one, most common with unsaturated hydrocarbons with those double or triple bonds that can open up to let new atoms in.
Got it. And lastly, what's a substitution reaction again?
A substitution reaction is when one functional group in a compound gets replaced by a different one. This is a common thing in saturated hydrocarbons where an atom or group trades places with another.
Fantastic. Now, before we dive into some specific carbon compounds, I have a question for our listeners. Thinking about those four reactions, we've talked about combustion, oxidation, addition, and substitution. Which one do you think plays the biggest role in your daily life? Take a moment to consider how these reactions might be happening all around you. All right, we've covered a ton of ground, from those basic building blocks to the reactions that carbon compounds go through. Now, can we get to the practical stuff, like what are some specific carbon compounds we encounter every single day?
Sure thing. Two compounds come to mind, ethanol and ethanoic acid.
Ooh, ethanol. Isn't that the alcohol we find in, like, beer and
Wow.
wine. But I bet there's more to it than just that.
Oh, yeah, way more. Ethanol is a pretty versatile molecule. It's a
Yeah.
great solvent, so it pops up in things like medicines and cosmetics, even cleaning products. And it burns pretty cleanly, so in some countries, they even use it as a fuel additive.
So it can power our cars,
Yeah, and you go.
clean our counters. Impressive. What about ethanoic acid? What's its claim to fame?
Well, ethanoic acid is more commonly known as acetic acid. And yep, you guessed it, that's the stuff in vinegar.
Vinegar. Gotta love it. But I'm guessing ethanoic acid does more than just make my salad dressing tangy.
You bet. It's super important for a bunch of industrial processes, used to make everything from plastics to textiles. And since it's a weak acid, it's a popular food preservative. Keeps things like pickles and salad dressings fresh.
Wow, so it's preserving our food and making our clothes. Carbon compounds are really the unsung heroes of, well, everything.
Absolutely. Now let's take a closer look at some of the cool reaction that these two can do. For example, ethanol can react with sodium metal and actually produce hydrogen gas.
Hold on, so there's a mini science experiment happening in my wine glass.
Not exactly in your wine glass, but yeah, you get the idea. Ethanol can also lose a water molecule and become ethene, which is key for making plastics.
So ethanol can make hydrogen gas and plastic. Wild. What about ethanoic acid? What kind of reactions does it get up to?
Ethanoic acid can react with alcohols to form esters.
Esters, right. Those are what give fruits and flowers their lovely smells, aren't they?
Exactly, those fruity and floral scents, often because of esters. Ethanoic acid and ethanol, for example, can team up to make ethyl acetate, a common flavoring agent and solvent.
So the sweet smell of a rose is actually chemistry in action. Amazing. And I remember from earlier, ethanoic acid being an acid means it can react with bases too, right?
You're on a roll. It neutralizes those bases and makes salts and water. Like with sodium hydroxide, it forms sodium acetate, which is used in food and even those hand warmers you use in winter.
Wow. Carbon compounds are involved in so much.
Yeah.
Before we move on, can you give us those final definitions one more time for ethanol and ethanoic acid?
No problem. Ethanol, aka ethyl alcohol, is a colorless, flammable liquid. Smells a bit sweet. It's the alcohol in drinks, but also a solvent fuel additive and used in a bunch of industrial processes.
And ethanoic acid.
Also known as acetic acid. Colorless liquid with a strong vinegar smell. It's a weak acid, found in vinegar, of course, but also used as a solvent, preservative, and to make plastics, textiles, you name it.
Great. Before we dive into our last topic, any questions for our listener about ethanol and ethanoic acid?
I do. Thinking about all the different ways we use ethanol and ethanoic acid, which application do you find the most surprising? And why?
That's a good one. All right, for our final deep dive, let's talk about something that's pretty important to all of us. Keeping clean. Specifically, soaps and detergents.
Ah, yes, those cleaning champions. Soaps and detergents are a perfect example of how we use carbon chemistry to stay clean and tidy.
I've got to admit, I never really thought about the science behind soap. It just, makes me clean.
Well, get ready to be amazed. Soap's cleaning power all comes down to its molecular structure.
Okay, I'm intrigued. How does soap actually work? Why can't we just rinse dirt off with water?
Think about the dirt on your skin or clothes. Most of it's oily. And as we know, oil and water don't mix.
Right, oil just sits on top of water, like those oil spills you see in the news.
Exactly. We need something to bridge the gap. That's where soap comes in.
Soap's the peacemaker. How does it do that?
Soap molecules are pretty clever. They have a hydrophilic head, which loves water, and a hydrophobic tail, which repels water but is attracted to oil.
So it's like a double agent working for both sides.
Yeah, that's a good way to think about it. When soap meets water, these molecules create tiny spheres called micelles.
The cells, wait, didn't we talk about those earlier?
We did. The hydrophobic tails, those oil-loving parts, they huddle together in the center of the micelle, far away from the water. The hydrophilic heads face outward, hanging out with the water.
So the oil-loving tails grab the dirt, and the water-loving heads help wash it all away.
Exactly. The micelles track those oily dirt particles and essentially make the oil mix with the water. Then when you rinse, the micelles, with the dirt trapped inside, go down the drain.
That's genius. But what about hard water? Doesn't that mess with soap?
Good point. Hard water has minerals like calcium and magnesium ions. These ions can react with soap and form those insoluble precipitates. That's soap scum.
That's why it's so tough to get a good lather in hard water, and why my shower gets that cloudy feel.
You got it. Soap scum reduces soap's cleaning power and leaves that residue behind. That's where detergents come in.
Detergents, okay. What's the difference?
Detergents are like soap in that they have those hydrophilic heads and hydrophobic tails, but they're made differently. The key is detergents don't react with hard water ions, so no soap scum.
So they're like Soap 2.0 can handle anything.
Haha, pretty much. That's why
Oh.
you see detergents in laundry detergent and shampoo, especially where the water's hard.
This is blowing my mind. I never knew there was so much to soap. Before we finish up, can you give us those final definitions for soaps and detergents?
Absolutely. Soaps are sodium or potassium salts of fatty acids. They're made by reacting fats or oils with a strong alkali, like sodium hydroxide. And they work because they have both hydrophilic and hydrophobic parts.
And what about detergents?
Detergents are synthetic, similar structure to soap, but made from petroleum products or other synthetic stuff. And they're great in hard water because their molecules don't form that insoluble precipitate with calcium and magnesium ions.
Great. One last question for our listeners, as always. Thinking about the impact of cleaning products on the environment, how can we make smarter, more sustainable choices when it comes to soaps and detergents? That's a great question to think about, and a perfect way to wrap up our deep dive into carbon and its compounds.
It's been an amazing journey, hasn't it? From the air we breathe, to the food we eat, to the products we use every day, carbon truly is the element of life.
Totally agree. It's incredible how one element can create such a mind-blowing variety of compounds.
And it just goes to show chemistry isn't just something you study. It's all around us, affecting every single part of our lives.
Couldn't have said it better myself. I hope our listeners enjoyed exploring the world of carbon with us as much as we did.
Me too. And I hope they learned a few new things along the way.
So listeners, next time you use anything with carbon, think about the power of this amazing element, whether it's the fuel in your car, the soap you wash your hands with, or the food you eat.
And remember, the more we understand about carbon chemistry, the better choices we can make about the products we use and how we impact the planet.
That's a fantastic message to end on. Thanks for joining us for this deep dive. We'll see you next time for another exciting exploration of the world around us.